Okay, so we have got another unit review, and this is our key. So, problem one, given independent events, A and B, such that the probability of A is 0.7 and the probability is 0.3, find these following probabilities. Okay, so the probability of A given B, if these events are independent, should just be the probability of A. That is the definition of independence. So this should just equal 0.7. If it didn't say they were independent, then we could find the probability of A given B by using the formula that's on your formula sheet of probability of A given B is the probability of A and A, no, I had it right the first time, A and B all over the probability of B, right? So the probability of A and B is going to be, for independent events, those things multiplied. But then if you divide by the probability of B, we end up back with the probability of A. So same thing goes for this. The probability of B given A, since the events are independent, should still just be the probability of B, which is 0.3. Okay. So the probability of A and B is, the probability of A or B, I'm using specific words. That's the union, so it's A or B. Either one will suffice. So that's going to be the probability of A plus the probability of B minus the probability of A and B. Now, what's fun here is this is asking for the probability of A and B. So let's find that first. Probability of A and B is the probability of A times the probability of B for independent events, which in this case is going to be 0.7 times 0.3 or 0.21. So when we go back to part C, we've got probability of A is 0.7 plus the probability of B, which is 0.3, minus the probability of the overlap, right? Because we don't want to double count the overlap. So that would be minus 0.21. And so that gives us 1 minus 0.21, which is 0.79. Okay. Again, not a lot of situations where you're going to have to calculate this like this, but it's important to have the basics. Okay, so next up. Number 2, data is collected on college freshmen's first semester GPA. The mean is 2.89, and the standard deviation is 0.38. The researcher then discovers that all of the collected GPAs were collected incorrectly and should be multiplied by 0.9 and have 0.7 added. Okay, multiply by 0.9 and have 0.7 added. So for the mean, we're going to multiply and add. For the standard deviation, like normal, we only multiply. So the new mean is going to be 2.89 times 0.9 plus 0.7. When we do all that, and make sure you're typing it into your calculator correctly, that is often a source of error. So the new GPA is actually 3.301. For a standard deviation, though, because again, it's a measure of spread, so shifts, pluses and minuses don't affect it, we're just going to take the 0.38 times 0.9. And that's going to give us 0.38 times 0.9, 0.342. Makes sense. 9.9 is 90%, so it's most of it, but a little bit less. Okay. Numero trois, part 3. Sugar Bomb cereal is including one of 5 Sherlock Holmes action figures in each box during a promotion. Okay, 1 of 5 in each box. Claire plans to purchase boxes until she has all 5 action figures. How many boxes should she expect to buy if each figure is equally likely to be in any box? Okay, first, and this is kind of a blast from the past, describe how we'll use a random number table to conduct this simulation. So I am, once again, going to use digits 0 through 9 with each corresponding to a particular figure, which I'm going to label as figures A through E. Then go through random number table and count the number of quote boxes, which in this case will be digits, until all 5 collected. And just for our purposes, I'm going to say 0 and 1 are figure A, 2 and 3 are figure B, 4 and 5 are figure C, 6 and 7 D, and 8 and 9 are figure E. Okay. And you can do this any way. It could be 0, 1, 2, 3, 4, and then 5, 6, 7, 8, 9. You can do it the way I did it. You could pick any 2 random numbers to go with each figurine. Doesn't really matter. The key is that each figure is equally likely to be in any box. So notice each of these figurines has 2 of 10 digits, so they're equally likely to be picked. So this is helpful for part B. Show 3 trials by clearly labeling the random number table given below. Specify the outcome of each trial. Okay, so I'm just going to write the letter of the figurine underneath each number until I've got all 5. For the sake of keeping track a little more easily, once I've already gotten a figurine, I'm just going to cross out the repeats. I'll still count them as the number of boxes, but it'll just help me keep track. You'll see what I mean. So 8 corresponds to figure E. 3 corresponds to figure B. 3 again corresponds to figure B again, so I'm just going to hold on to that. 7 corresponds to figure D. 4 corresponds to figure C. 5 also corresponds to figure C. 2 corresponds to figure B, which we've already got over here. Another 2, figure B. 9, figure E. 7, figure D. And 0, figure A. So here is trial 1. And it took 11 boxes. And I know it's 11 because each of these groups is of 5. Cool. Now we go again. So 7, that is going to be figure D. 7 is figure D. We have that already. 6 is also figure D, which we already have. 9 is figure E. Here's a bunch more E's. Here's another D, another E. 2, here's our first B. We've gotten a bunch of 7s already. And that one's figure E. This is our first 3, but it's also a figure B. 6 is also a figure D, which we have. We are looking for C's and A's at this point. 5 is a C, so here's our first C. 9 is an E, 3 is a B, 4 is a C, E and D and D and B, and 7 is another D, 5 is another C, 3 is another B, and we keep going, and here's finally an A. That took a ton of boxes. So hang on. We've got 1, 2, 3, 4 full sets of 5. And then there's 4 here and 4 here. So that's going to be trial 2 is 28 boxes. Oof, poor Claire. Lots of cereal. I hope she has a good dental insurance plan. All right. Now, 3 trials. Trial 3, I hope we have enough. So 6 is D. Here's an A. Here's another D. Here's a B, another A, another B. Here's a C. Okay, good. And here's an E. All right, sweet. That worked out. So this is 1, 6, 10. So trial 3 is 10 boxes. Okay. So obviously this is very tedious. And it's the sort of thing where you won't have to do more than 3 or so trials, maybe 5, but I'd be surprised. Certainly not on one of my tests, but it's good to know how to use a random number table. Okay. Now we get into some of the new, binomial geometric stuff. Let's say Claire thinks Watson is the best character, obviously. If the random variable W represents how many Watson figures Claire finds, is W binomial? Why or why not? So I would say yes, because it's either Watson, which is going to be our success, or not Watson, which is going to be our failure. Remember, binomial can be defined as success and failure. The one caveat being there's not a fixed number of trials, not a fixed number of trials. So we could set this up like if we said in 20 boxes, what's the probability that Claire finds 6 Watson figures or 2 Watson figures or whatever we're looking for? That would definitely be binomial. So I'm going to put an asterisk with this. Yes, we can turn this into a binomial question by defining Watson as success and not Watson as failure. But there isn't a set number of trials yet. Okay, so how many boxes should she expect to buy before she gets her first Watson figure? Every time you see that word expect, think mean, right? Mean, expected value. These are all the same thing. So essentially, so let me just pull up. I'm going to use the formula sheet as well. So the mean of a binomial situation, this one, of course, is just that the mean of X is equal to the number times the probability. So there's 5 action figures. That's what I was circling up here. So there's 5 action figures. So she, and they're equally distributed. So she has, oh, excuse me, before, let's back that up. For a second, I was like, wait, where does the n come from? So this is still going to be a mean, but now this is going to be geometric. So this one, the mean, is going to be 1 over the probability. And we know this because before she gets her first Watson figure, her first success, I got a little ahead of myself. So we need to do 1 over 1/5. And that's just going to be 5. So she should expect to buy 5 boxes. Okay. E, what's the probability that Claire's first Watson figure will occur after the 3rd box? So this is the probability that X is greater than and after, so greater than 3. And because our geometric and binomial distribution functions are, or density functions are giving us what's to the left, we need to think about how do we find what's to the right. So the probability of everything always adds up to 100%. So we're going to do 1 minus. And this is first, so it's about when, so it's geometric. And it's after the third box. So this is going to be a CDF because it could be the fourth box, it could be the fifth box, etc., etc. And the geometric CDF, the probability is 0.2 or 1/5. And the number we're taking out is 3 and below. So because we're not including the third box here, because there's no or equal to, I'm just doing 3 here because this represents right here the probability that the first success occurs on the first box, second box, or third box. So if we want what's after, we need to take those first 3 out. Okay, so probability is 0.2, x value is 3. We're going to do 1 minus. Okay, so this is 0.512, about a 51.2% chance. Makes sense. We're expecting to buy 5 boxes before we get the first one. 50% chance she'll have to buy more than 3. Cool. That gels. Okay. Now we get into our binomial situation. If Claire buys 9 boxes, this is our fixed number of trials. What's the probability that she gets exactly 3 Watson figures? So exactly, this is our PDF. So this is going to be binomial PDF with 9 trials. Binom PDF with 9 trials. Probability of 0.2. Oops. And the x value is 3. So this is our trials. This is our probability. And this is our x value. And so you could even set it up that the probability that x is equal to 3 is that. So again, the equal sign is matching up with the PDF. So trials 9, P is 0.2, and x value is 3. So exactly 3 Watson figures out of 9 boxes. That gives us a 0.176. So it's about a 17.5% chance that she gets exactly 3 Watson figures out of 9. Okay, so very similar, but not the same. She buys 9 boxes. What's the probability that she gets at least 3 Watson figures? So at least, now it's not an exact value. We're going to use our CDF function. And so we're looking for the probability that x is greater than or equal to 3. Now, that or equal to is important here because at least 3, which means 3 is satisfactory. So it's a greater than, we'll do a 1 minus. It's an at least, so there's a range, there's an inequality. It's going to be CDF. The number of trials is still 9. The probability is still 20%, 1/5. But here we want to do 3 minus 1 because this is the number of trials. This is the probability. This is the it's the x value, but it's also basically the outcomes that don't work for us. Outcomes not satisfactory. So at least 3 means 3 works, which means what we want to subtract out here is the possibility that she gets 0 Watson figures, 1 Watson figure, or 2 Watson figures. So that's why this is going to end up as a 2. So binomial CDF, 9 trials, probability is 0.2, and the x value is 3 minus 1 or 2. So if she buys 9 boxes, the probability that she gets at least 3, so 3 or more, is 0.262. about 26%. So you could do that with a bunch of PDFs by doing the PDF of 3 boxes, the PDF of 4 boxes, of 5 boxes, of 6 boxes, of 7 boxes, 8 boxes, 9 boxes. That is one way to do it. And that's what you would have to do if you're doing this by hand with the N over K, etc. That's really not necessary. So H, if Claire buys 9 boxes, what's the probability that she gets at most 3 Watson figures? So fixed number of trials again, at most. So at most includes 3. So unfortunately, these aren't quite complementary. We can't just do a 1 minus off this because 3 is included in both cases. We could do a 1 minus of that and then take out that as well, because that's exactly 3, but we can do this in one fell swoop as well. So here we're looking for the probability that X is less than or equal to, because again, 3 works, 3. Since we want a less than, we don't need to do the 1 minus. Since it's a range, we have an inequality here. This implies a range of satisfactory values. We're going to use CDF. So it's a binomial cumulative density function. The C is for cumulative, right? All of them. And we'll say 9.2. And here, we're just going to leave this at 3 because in this case, 3 is acceptable. And we're not taking anything out, so we want to include it. So we've got 9 trials. Oh, got a label. This is the probability, and this is the X value. And that puts us at 0.914. So again, if you were interested, another way you can get there is by doing 1 minus 0.262. So this is this was the probability of getting at least 3. And let's see, 1 minus, yeah, that was, sorry, I still have it in my calculator. So we're going to do that plus that. Yeah. So this is 0.738, and I misspoke earlier. We're not going to subtract this out. We're going to add it in. And this is the probability of getting 2 or fewer. And so we're going to add 0.176, which is the probability of getting exactly 3. And we get right back to 0.914. Again, if this makes sense, you're in really good shape. If this did not make sense, that is okay. I'm happy to go over in class. All right. Claire went nuts and bought 100 boxes. Okay, it's too much cereal. Would you be surprised if she got fewer than 10 Watson figures? Justify your answer. Okay. Anytime it says justify, this means show the math. Actually do the work. So let's just calculate the probability that in 100 trials, we're going to get fewer than 10 Watson figures at a 20% chance of getting a Watson figure on any given box. So fewer is to the left. So the probability that X is less than 10, right? 10 is not included, so fewer than 10. And so this one is going to be a binomial CDF because fewer again implies a range. So we've got our cumulative density function. Scooch this down. Bloop. Okay. And the number of trials this time is 100. The probability is still 0.2, but this time fewer than 10. So we don't want to include, hi Kat. We don't want to include 10. So we're going to look for 1 less than 10 or 9. So again, this is our trials, this is our probability, and this is our X value, or the number of successes. Okay, so when we pop that in, second vars, binomial, CDF, trials 100, and the X value is going to be 10 minus 1, or not. And so we get a 0.002. So there is a 0.2% chance that if Claire bought 100 boxes, fewer than 10 would have Watson figurines. So yeah, I would be surprised. Anything less than a 1% chance is pretty unusual. Okay. Cool. Next up, multiple choice. Oh, thank goodness. I love some multiple choice. Target wants to collect some information on its customers. Which of the following situations is a cluster sample? So cluster sample, remember, is all of some. So we're going to pick some locations, groups, whatever, randomly. It has to be picked randomly. And then we're going to survey all of the people in that cluster, or all of the subjects in that cluster. So a random sample of 50 stores and survey every customer at those stores. That's looking pretty good. However, multiple choice, you should always read every single answer choice. So next up, pick the 50 closest stores to headquarters and survey the customers at those stores. Nope, that would be called a convenience sample. That's a terrible way to do anything. Unless, you don't care about being statistically accurate and you would save money. C, survey every 100th customer at each store. This would be a systematic random sample. D, from a list of Target Rewards customers, randomly select 500 customers to survey. So this is kind of a simple random sample. However, from a list of Target Rewards customers, that is not a representative population, or it's not representative of the population of customers. If they wanted to talk about Target Rewards customers, sure. But if we're narrowing this population, it cannot apply to customers as a whole. So this is out for a couple of reasons. Lastly, split the list of Target Rewards customers into males and females, then randomly select 500 males and 500 females to survey. So this could be a stratified sample, especially after the split it into males and females, then survey 500 of each. But this has the same problem. List of Target's Rewards customers, not a representative sample of our population. So everything but A is either something else or bad. So it's got to be A. But always read all the answer choices, because sometimes you've misread the first one and you don't catch it until you say, wait a second, there are two answers that work here. Or sometimes you're like, wait, all of these work. And then you realize you completely misunderstood the question, and the only one you crossed off is actually the answer. Boop. All right. Numero 5, number 5. Costs for standard veterinary services at a local animal hospital follow a normal model with a mean of $56 and a standard deviation of 450. Welcome back to normal world. Approximately what percent, so we want a percent, we're going to use a CDF function, of services cost less than $51. Cool. Always going to draw a little picture. Blue. I'm going to put my mean right in the middle here at 56. And 51 is just a little bit below one standard deviation. And what I want then is less than 51. I like to draw these pictures because the shading helps me think about what are my upper and lower bounds. So we're going to say normal. It's normal. Normal. CDF. Our lower bound is going to be negative infinity. Our upper bound is going to be 51. And I'm setting those as lower and upper because we want what's less than $51. Our mean is $56. Baby, don't. Sorry, my cat. And then our standard deviation is 450. As usual, we're going to label everything. So this is our lower. No, oh my gosh. And my cat has officially crawled into my backpack. This is our upper bound. And this is our mean. And this is our standard deviation. Okay, so I'm going to pop that straight into the calculator. Normal CDF, our old trusty friend. And we get about 13%, which kind of makes sense, right? It's a little bit more than one standard deviation below the mean, but not a huge amount. It's definitely not 2 standard deviations. So there's a decent chunk of services right in there, but it's not huge. So about 13% makes sense. So for B, same idea, but other direction. What percent of services cost more than 67? I'm just going to put 56 in the middle. 67 is going to be 11. So almost 3 standard deviations. So I'm expecting this number to be really small. I am going to be bad and not label my normal CDF. I'm just going to write what I'm putting in because I don't have room. So my lower bound this time is going to be my point of interest because I want to know what's more than 67. My upper bound is going to be positive infinity, or the best approximation. Mean and standard deviation are the same. And when we do that, we get 67. And make sure when you're putting that E in that you're using second and then the button above the 7. If you use the letter E, you're going to have not a huge upper bound or huge lower bound, and that's going to give you errors. So this comes out to 0.7%, so 0.007. So that's really low. And that makes sense, right? We were a bunch of standard deviations above the mean here, so we would expect it to be pretty far out. Okay. Let's get through number 6, and then we'll take a break. So at PHS, 7.4% of students have a December birthday. If a random sample of 50 students is selected from all students at PHS, what is the probability that at least 9 will have a December birthday? So again, this is at least will have this thing. This is binomial, December or not December. So we're going to say binomial. It's a CDF because it's an at least. Remember the probability that X is greater than or equal to 9. And the number of trials is 50 because we're selecting 50 students, or sample size could be considered the number of trials. We're selecting 50 students. The probability of having a December birthday at PHS is 7.4%, 0.074. And then greater than or equal to 9. So it's a greater than, I forgot my 1 minus. And we want to take out everything 8 and below. So we're going to do a 9 minus 1 here because we want what's left over. That's why we're doing the 1 minus. So we don't want to take out 9. We do want to take out 8 and below. So 1 minus binomial CDF, 50 trials, 0.074 as our probability, and our X value is 9 minus 1, or 8. And so that gives us a probability of 0.01. So about 1% chance that at least 9 will have a December birthday. So 9 or more. It's kind of the same situation, but fewer than 3. So the probability that X is less than 3 will have a December birthday. So it's a less than, we don't need the 1 minus. It is a range. So we're going to do a cumulative density function. And in this case, it's the same number of students, the same trial of 50. It's the same probability. But here, fewer than 3 does not include 3. So again, this is going to be a 3 minus 1 situation. When we do all that, so second this. And X value is going to be 3 minus 1 or 2. And so there is a 27.4% chance or 0.274 chance that fewer than 3 will have a December birthday. Makes sense. The expected number, even though it's not a question, the expected number to find would be 50 times 0.074, which is 3.7. So our expectation is, 3 or 4 of those 50 students have a December birthday. So fewer than 3, 27% chance. That's not crazy. Okay. So let's pause there. I would like to drink some tea, and I'll finish this later.